Good morning everyone, hope you're all well. It's Dr. Bennett here again, and today we're going to do the second part of our review of the semester in preparation for the final exam. So just to reiterate, the final exam is on the 29th of April, and it will be between 8 AM and 10 AM, so a 2-hour window between 8 and 10 in the morning. So this is the document that I started referring to last class. We did all of this stuff here in blue on Monday. I've made a couple of changes to this document, and I've uploaded the most recent version to Canvas, so you can use this as a checklist, as I say, to revise for the exam. So this can be found in files under online course notes. It's down here, look. This is the checklist, the Word document, and this is a PDF of the notes that I've been talking through. So today we're going to start off with the second part of systems in equilibrium, and then we're going to go on to look at some of the more recent stuff that we've looked at in the course. Most of this stuff here has been covered since we moved online, so if you'd like to go back and re-watch any of those videos or re-look at the notes, it's all up there on YouTube. So let's kick off with the second part of systems in equilibrium and applications of equilibrium equations in 2 and 3D. Got some tea on the go. Alright, so here we go then with part 2 of systems in equilibrium. We're going to start off by quickly revising how to apply the equilibrium equations. We're going to do an example in 3D that also revises 3D supports, right? So we talked about supports in 2 and 3D in the previous review class. Now we're going to use that information to resolve a system and apply the equilibrium equations to a 3D system. So if you'd like to go back and have a look in your notes, we did an example similar to this to do with hinges. That was example 5.9 from the textbook. We did this in class. We went through this. We reduced the system down based on the information we were given in the question about these two hinge supports, and we worked through this example to find the reactions due to those hinge supports. So that's quite a good one because it's a worked example from the textbook. It's a good one to go through to revise how to apply the equilibrium equations to a 3D supports problem. What we're actually going to do now is something similar to that, but with different supports. We're going to have a look at this example 5.7 from the textbook, which is to do with this ball and socket support in 3 dimensions, and we have this beam which is supported by ropes or cables attached at point B, which is at the end of the beam, to the walls. So we're told that this cable BC is parallel to the z-axis and BD is parallel to the x-axis. So that means that we're only going to consider the tension in these cables in one dimension, or parallel to one of the axes, right? So that's going to make our sum of the moments, as you will see when we come to look at the moments, a little bit more straightforward. The only other external force that we have applied to this beam is the 200 Newton force in the negative y direction. So the question is to find the reactions at A. So the first thing I've done is drawn a free body diagram of that beam. So you'll remember the ball and socket support in 3 dimensions is kind of like the pin support in 2 dimensions, where it prevents translation, so the support can't move about, but it allows free rotation of the arm. So we have 3 reaction forces but no moments. Then I've just got my 2 unknown tensions in these cables, which, as we said, were parallel to the Z and X axis respectively. And then I've also drawn on the negative 200 J Newton force acting at the midpoint of the beam. So I've got a coordinate system, I've got all of my force vectors, and I've got some dimensions on there. So this is a complete free body diagram. I've got 1, 2, 3, 4, 5 unknowns. It's a 3D system, so I can apply 6 equilibrium equations, and therefore the number of unknowns is less than the number of equilibrium equations which can be applied, and therefore we can solve it because it's a statically determinate system. So what I've done then is summed forces in the X, Y and Z directions. So in the X direction I just have positive this and negative this. In the Y direction I have positive this, negative this, and in the Z direction I have positive this and negative this. So I can solve this middle equation for FAY, that's no problem, but I need to sum the moments about some point in order to solve for FAX, TDB, FAZ and TBC. So this is the new bit then, this is the tricky bit with this, and I've seen a few mistakes in homework assignments and stuff like that. When we come to sum the moments in 3D. So if we're summing the moments about point A, which is recommended because that eliminates these 3 reactions, then we're going to have a moment exerted by this force, the negative 200 J Newton. We're going to have a moment exerted by the tension in the cable BC, and we're going to have a moment exerted by the tension in cable BD. Right, so we're going to have 3 pieces to the sum of the moments, right? So you'll remember from the last review class, or from previously, that moment is a force times distance, right? So we know the magnitude of these forces, or we'd like to find them. So all we need is a perpendicular distance from the point where we're assessing the moments about to the point where the force is applied, right? So in the case of this 200 J Newtons, it's applied halfway along AB. So we need half of the position vector AB, cross product that with the force vector. So I've done that for each of these. So the TBC force vector is in the negative Z direction, so I've got a negative K component here, and the TBD force vector is in the negative X direction, so I have a negative I component here. So if I work out what the position vector RAB is, it's straightforward because A is located at the origin. Then I've got 3 cross products that I can calculate, and then I end up with an equation that contains I's, J's and K's. And what I do to get my 3 further equilibrium equations is to separate the I's, J's and K's into 3 further equations. So the I's go into the sum of the moment about the X, the J's go into the sum of the moments about the Y, and the K's go into the sum of the moments about the Z. And that gives me my 6 equilibrium. Remember we said 6 equilibrium equations in 3D. This is 3 of them, and this is the other 3. So So I can solve for my 5 unknowns using those 6 equilibrium equations and find the reactions at A and also the unknown tensions in the cables BC and BD. So just be sure that you can follow through that solution method and that you can get the example, the solution given in this box in the textbook. So if you're able to do that, that's quite a good example and a good revision of how to apply the equilibrium equations in 3 dimensions. So what's next? Let's have a quick look at what a two-force member is. So you'll recall a two-force member is when we have forces or reactions applied on a member, and we assume that the external forces that are applied to this member are equal in magnitude, so F and minus F, opposite in direction, so either stretching it out, so giving it some tension, or compressing it in, right? And has a common line of action through the center of the member, through the points where both forces are applied. So if all of those 3 conditions are satisfied, then this two-force member is in equilibrium. And what we do is we use these assumptions when we deal with trusses, frames and machines, so that we're able to solve and analyze those systems. So looking at trusses then, we have 2 potential solution methods to use depending on what is most convenient for us, depending on where we're looking to find the unknown axial forces. So the first method that we have at our disposal is called the method of joints, and that's where we isolate a single joint of the truss and then we find the local axial forces around that joint, and then we're able to move around the truss systematically to solve for all of the unknown axial forces. The second method that we have is called the method of sections, and that's where we make a cut through the truss somewhere because we're only interested in the axial force in one specific member. So in that case, if we're only interested in finding the axial force in one member that's sort of in the middle of the truss, and we don't want to apply the method of joints and go systematically all the way around, we can save ourselves a bit of time and make a cut through the truss structure just to find the unknown axial forces in one specific member. Now, if we're using the method of joints, we can cut at most 2 members, right? So if we want to find the axial force in this member here, AD, we can isolate joint A and then only cut these 2 members, right? And because we only have one joint on the left hand side, right, we can only apply 2 equilibrium equations. We can apply the sum of the forces in the x direction and the sum of the forces in the y direction. We can't sum moments, right, because we don't have anything to sum moments about, because we only have one joint, right? So therefore we can only cut 2 members. On the other hand though, if we're doing the method of sections and we make a cut, we have more than one joint on any given side of the cut, and therefore we can sum moments about a point, and therefore we can cut 3 members this time and not just 2. So with that in mind, we're just going to have a quick look at this example here. I've drawn a Freebody diagram of a truss, and I've got some dimensions on there. I've got some external loads. I'm assuming a pin support at A and a roller support at K, And what I'd like to do is find the axial forces in AD and GJ. So the first thing that I have to do is apply the equilibrium equations to the whole truss to find the unknown reactions. Right, so once I know those three reaction forces, then I can go ahead and apply either the method of joints or the method of sections. Now, as we've just discussed, the method of joints for AD is the most appropriate method, because I just go ahead and isolate joint A, and if I know from the application of the equilibrium equations to the whole truss, if I know the reaction forces in the x and y direction, then I have just two unknowns, TAD, TAB, and therefore I can apply these two equilibrium equations to find them. So that's straightforward. To find the axial force in GJ, I can use the method of sections and make a cut through the truss structure through here, right? Cutting 1, 2, 3, right? Cutting 3 members. And therefore I've drawn a sub-Freebody diagram of the right hand side, which contains joints K and J, right? So I'm cutting through here. So therefore I have unknown tensions in JG, JI and KH, which I've drawn here. So again, if I know FKY, which is the reaction due to the roller support at K, then I have just 1, 2, 3 unknown axial forces, and therefore I can apply 3 equilibrium equations to solve them. So that's just a quick review of how to solve trusses in 2 dimensions. If you'd like to have a further practice at that, I recommend looking at example 6.36 from the textbook. So let's move on then to trusses in 3 dimensions. We call them space trusses, you'll recall. We did an example of this in class, and there's also a video on YouTube of a complete rundown of one of these examples. We're just going to have another quick look at this example, which is 6.5 from the textbook. We have a 3-dimensional truss structure that's kind of like a triangular based pyramid type shape. We're given some dimensions, or we're given coordinates of the joints or the nodes of the truss structure. We know that the point B is at the origin, and basically we have all roller supports on the surface. So if we can consider the plane XZ as like a surface, we have 3 roller supports. I'm actually looking in the textbook for the Freebody diagram. Let me quickly skip back in the textbook. I'm looking for example 6.5, yes, this one, right. So this is the example that we're looking at. We have B at the origin, these are all roller supports, and then we have this externally applied load at point A of 1,200 pounds. I've called that 1,200 newtons because I'm dealing in newtons and meters. But the example is the same. Because I've got roller supports, then I only have reactions in the y direction, right, at each of these points. So the application of the equilibrium equations to the whole truss is actually quite straightforward. I have no forces in the x direction or the z direction, but I need to solve this equation here for the forces in the y direction. So because it's a 3D problem, I need to find my 6 equilibrium equations again, right? So if I'm summing moments about B, I've chosen B to sum moments about, not because it eliminates any more forces than any of the others, but because it's located at the origin, and therefore all of my position vectors are all with respect to the origin, so that just makes the maths a little bit easier for the position vectors. So if I'm summing moments about B, I have a moment due to the reaction at C, I have a moment due to the reaction at D, and then I have a moment due to this 1200 Newton force acting at A. So I work out each of those position vectors, and then I cross product them with the force vector. So these three force vectors are only in the y direction, so that's why I've just got j's floating around here. I've got no i's and k's, right, because I've got no forces in the x or z direction. So as we've just seen in an example just now, we solve those cross products, get an expression in terms of ij's and k's, separate the i's, j's and k's to form the three further equilibrium equations for the moments in x, y and z. And then I have three equilibrium equations here and the further three here, giving me 6 to solve for those unknown reactions. So once I know the reactions, I'd like to find the axial forces in these highlighted members, so dA, dB and dC. So what I can do is go ahead and isolate joint D and then draw a sub Freebody diagram of what that looks like. So here I'm assuming that I've found my reaction at D, right, so that's known right now, and then I have an unknown axial force in dA, dB and dC, which I've labelled TdA, TdB and TdC. So then what I do, so I'm looking for the magnitudes, right, of those axial forces, but I don't know the directions yet. So I write TdA as the magnitude of TdA multiplied by the unit vector in the dA direction. So I need to do some algebra here to find, first of all, the position vector dA, then scale it based on its magnitude to find the unit vector. So I will have equations for TdA, TdB and TdC and their components, right, based on the unit vectors, and then I can separate those into the sum of the forces in x, y and z. That will give me 3 equilibrium equations and 3 unknowns, and therefore I can solve for these unknown magnitudes of the axial forces. So again, please make sure that you're able to solve that type of problem. You can follow the example through in the textbook, so this is on page 278, 279, and follow the method as I've just described it to try to find these unknown axial forces down here. Make sure you can get the same solution as the textbook. So that's 2 and 3D trusses. Let's finally have a look at frames and machines to complete this section. So you'll recall that a frame is kind of like a truss, but not all the members are supported or loaded at the joints, and therefore they're not all 2-force members. So we have to apply a slightly different approach to solve a frame question. And a machine is a frame which is designed to move. So like we saw some examples of some tools, some like machinery, some like gym equipment and that kind of thing, right? So what we're going to do is have a quick look at example 6.6 from the textbook, which is on page 290. So we're going to have a look at this question, which asks us to find the forces and couples acting on this frame. So we have a fixed support at A, we have one member going across here joined at B to this member, which is supported by a roller support. It's got this externally applied couple or moment on the member BC. So that's what tells us that it's a frame. So the first thing I've done, as always, is draw a free body diagram. I've got a fixed support at A, and therefore I've got reactions in the X and Y and also a moment. And then I've got this roller support C, and then this externally applied couple. So this is C down here, isn't it? So I've got coordinate system, I've got dimensions, I've got my force vectors and moments. So the first thing that you will realize here is that we've got a statically indeterminate system if we try to solve it as is, because we have 3 unknowns over here and this is a fourth. And for a two-dimensional problem, we can only apply 3 equilibrium equations. So immediately we have a problem, and that's because this is a frame and not a truss, right? Because we have this. So the technique for solving this is, hopefully you'll remember, is to draw free body diagrams of the members separately. So I'm going to draw a free body diagram of AB and a separate free body diagram of BC. And then where these two members are in contact, I'm going to have equal and opposite reactions. So I've chosen to draw them both positive for AB, so therefore they're both negative for BC, right? So these are opposites. So now what I have is, for member BC, I now have only three unknowns, right? I have the reactions at B and the reaction due to the roller support at C. So I can solve this side first, right? I can apply 3 equilibrium equations over here to solve for these 3 unknowns. And then once I know FBX and FBY, then I can put them into this side, and then I only have 3 unknowns over this side, right? So that's the technique for solving this frame, is deal with the members separately, work out which one you can solve first, in this case this side, and then put the knowns into here, and then therefore solve for these unknowns. So that's it for the first section on systems in equilibrium. We're now going to move on to the next chapter, to review the next chapter, which is all about centroids and volumes and moments of inertia and that kind of thing. Alright, so now let's move on to shapes and volumes, starting with centroids of areas and compound areas. So you'll remember I described this in terms of, so let's take the x-coordinate of the centroid of the area of this blob. What we're finding here is the point where, if I place this shape on like a seesaw, like a fulcrum point, I'm finding the x-coordinate where the left-hand side would balance the right-hand side, right? So that's the concept, and this is useful for finding centers of mass, or finding the point at which the weight of an object acts, right? If we want to consider it as like a point vector, like a single point force. So we derive these equations here, the integral equations, and so this finds the coordinates of the centroid in a two-dimensional system, where this quantity dA is the area of a strip of width dx. So you remember we derived these by dividing these shapes up into infinitesimally small strips of width dx and then summing over the whole area. So what we did in class, we looked at a couple of examples. I'll remind you of how to find this quantity dA with these little examples here. So we have the area bounded between the lines y equals x and y equals x squared. Well, what happens when we split it up into little strips of width dx? the height of those strips is just going to be the difference between the two lines, right? So y equals x is always on the top, so the height is x minus x squared. So then the area of each of those little strips is just the width times the height, right? So that's where I've got this from. And then once we have the quantity dA, then we can just plug that straight into the equation for the centroid of the area. So here y equals x and y equals x squared cross when x equals 1, right? So I'm integrating between x equals 0 and x equals 1 of x multiplied by dA, which I've just found here. Similarly to that, we did an example looking at finding the coordinate of the centroid of this triangle. So again, we split it up into little strips of width dx. The height of the triangle or the strips is given by the line defining the triangle, right, which is 2x. So then dA is just width times the height again, and then again we are plugging this into the equation for the centroid. So what about compound areas then? Well, if we had compound areas such as this that was attached to something else, then we'd have to use the integral equations to find all of these little x bars in here, and to find the areas of each of those individual pieces. But what we were dealing with in class was looking at the centroid of the area of compound shapes which are made from typical shapes that we can look up results for in the appendix, right? So if we have some simple shapes stuck together, it's called like a compound area. It's quite obvious what's going to happen here if these two triangles are basically mirror images of each other. Then the centroid of the area is just going to be in the center. But what we do is we look up the centroid of each of these pieces, calculate the area, and then sum the product of them, and then average that over the whole area. So that should be fairly intuitive. The only thing that you need to watch out for when you do this is when you find the x-coordinate of the centroids of the pieces that have been shifted along the x-axis. So like here, x2 and x3, we'll look up in the appendix the centroid of a square or a rectangle, but then we need to remember that it's been shifted by a certain distance along the x-axis. So that's the only thing to look out for in here. Again, make sure that you're comfortable using the appendix in the textbook, because that's where we're going to get all of these standard results from. And then this example here, where we have a shape with a cutout, we do the opposite thing, right? So we find the x-coordinate of the centroid of the whole shape, we find the x-coordinate of the centroid of the cutout, and then we do one, subtract the other one, and then average that over the difference in areas, right? So that's all to do with centroids of areas. Then we went on to have a look at distributed loads. So just to remind you what a distributed load is, it's basically us saying that we have some load which is spread over the length or partial length of something that's supporting it. Like, so think about like a car on a bridge or something like that. We have some length that's associated with how the load is being spread on that particular support. And typically what we have is, say we have some shape of the distributed load, right? We call how that shape is described with this notation W, which is some function of x, and that's called the loading curve. So that tells us, that loading curve tells us how this load is being distributed over some member, right? And we can find the magnitude of the force and the magnitude of the moment acting on that member due to that distributed load. And how we do that is we integrate the loading curve with respect to x over the length of which it's being applied. So that's for the magnitude of the force. When we do the magnitude of the moment, obviously there's a length associated with that as well, so we have to multiply the loading curve by an extra x. So the one thing to remember about these formulae is that they are magnitudes. We don't have directions here, right? These will always be positive. So we need to look at the original diagram to assess the direction of the force and the moment. So you'll remember that example that we did, I think it was in the homework, wasn't it? About the distributed load that profiled the lift on a wing. So obviously the lift was acting upwards. So we had a positive force in the y direction for F, and then we would have had a counterclockwise moment, right, about the wing root. So just be aware that these will always be positive, so you need to assess on the original diagram which way that they're acting. So let's have a quick look at this example here. We have a loading curve described by y equals square root of x, and we have a fixed support down here at A, which I'm calling the origin. I also have 100 Newton force acting upwards at a distance of 20. These can be meters for convenience. And also this couple, counterclockwise couple of 10 Newton meters acting on the member as well. So to find the reactions at the fixed support at A, the first thing we need to do is find the magnitude of the force created by the distributed load. And we do that by using these formulae, right? So in this case, we integrate the loading curve, which is root x, between 0 and 10 to get the magnitude of the force. Now the arrows are pointing downwards, so that tells us it's going to be a force in the negative y direction when we come to apply our equilibrium equations. And then to find the magnitude of the moment, we do the same thing, but we multiply it by an extra x, right? And this is going to give us a clockwise moment about A. So that's going to be negative when we come to sum our moments, right? So the other very important thing to remember about this is that this moment is the moment due to this force. So that when we apply the equilibrium equations, we need to remember to include either one or the other in the sum of the moments, right? Because this is the moment due to this force, so we don't need to include them both. So in this example here, I've summed forces in the x direction. I just have FAX, so that's 0. In the y direction, I have FAY. I have this 100 Newton force, which is positive, and then I have the F, the magnitude of the F in the negative direction, which I've calculated here. And then summing moments about A, which I'm assuming is the origin, I have MA, the couple exerted by the fixed support. I have the clockwise moment about A, which I calculated here, so that's going to be negative. I have the 10 Newton meter force here, and I also have the moment due to this 100 Newton force acting at a distance of 20. So just make sure that you are happy with resolving that. As I say, the only things to remember here are that this is the magnitude of the moment due to this force. So down here, we only need to include this. And because this is only the magnitude as well, we don't have a position, we don't have an x-coordinate of the centroid. We could work it out, but using this equation here, we only know the magnitude of the force. We don't know the position at which the force vector is actually acting, right? So it's going to be more towards 10 than it is to 0, and we could work that out, but we don't have that information here, so we wouldn't be able to include it in this equation anyway, right? So what I'm saying here is, in the sum of the moments equation, use this, not this, right? And definitely not both. Then we've moved on to look at centroids of volumes and lines. So similar kind of technique to working out centroids of areas. The formulas are very similar, but this time we've got dVs in here instead of dAs. So remember when we said the dAs were just the areas of the little strips of width dx? Well, these are the volumes of the little strips dx now, because we're working in 3 dimensions. And we find dV by taking the cross-sectional area. So for example, in this case, the cross-sectional area of this cone shape, right, is going to be a circle. Take the cross-sectional area, multiply it by dx. So the cross-sectional area, as I said, is a cross-section of a circle, so that's pi r squared. So multiply it by dx and we get dV. So that's how we deal with volumes. The technique for solving a problem is exactly the same, apart from we're now dealing with dVs and not dAs, right? We have an extra degree of freedom, but the technique is exactly the same. When we're dealing with centroids of lines, again, very similar formulae, but this time we've got dLs floating around, where dl is the length of the line that we're trying to calculate the centroid of. And we calculate that by saying, well, we do a bit of trigonometry, right? We say that dl is the square root of dx squared plus dy squared, which we can rearrange into this formula here. So all I've done is taken dx out so that I can calculate the derivative of the equation of the line that I'm given and stick it into here. So that's what I've done here. I've said dy by dx of x cubed is 3x squared. If I square that, I get this, and therefore using this formula here, I can say dl is the square root of 1 plus 9x to the 4 multiplied by dx, and now I have an equation in terms of dx that I can put into here and integrate x with respect to dx. And by the way, one thing to remember as well is that the centroid of an area or a volume or a line isn't necessarily on the object itself, right? So in the case of the line, y equals x cubed, it's clear that the centroid of the line is going to be over here somewhere, right? So that's something to be aware of as well. Don't get too spooked if the answer that you get is not actually on the line itself. If it's got some curvature to it, it may not be. And then we looked at doing some composite volumes. Again, this is the same technique as looking at composite areas. You just take the centroids of typical shapes that we know, whether it's cylinders or cones or whatever, and then use that sort of averaging formula that we showed for areas. So what was next? Next, we went on to look at the Pappus-Guldenius theorems. And these theorems give us results to work out the surface area of a revolution and the volume of a revolution. So say that we've got some shape or some line defined in a two-dimensional space. Well, we can rotate it about the x or y axis, and then we get a shape created when we do that. So a couple of things to remember about applying these formulae. When we're dealing with the surface area of a revolution, this y bar coordinate here is the centroid of the line being rotated, and this is the length of the line. So in this case it would be the line L that we're rotating. We would find the centroid of the line L, which will just be halfway along it because it's a straight line, and the length of the line we can just work out using trigonometry. But then when we deal with the volume of a revolution, we're essentially dealing with an area that's been rotated around the x-axis. So in this case, a triangle, right? And in that case, we have to find the centroid of the area being rotated, not the line, right? And then the area of the shape being rotated. So in this case, we'd find the area of the triangle and then rotate it around the x-axis. So the Q for remembering which way around these are is L for line and length, right? And therefore we find the centroid of the line. Here we're dealing with A and areas, and therefore we find the centroid of the area being rotated. So in this example here, I think we did something similar, if not the same as this in class, but we have some generic cone of height h. This length here is L, defining the shape of the cone, and the end of the cone has got radius capital R. So to find the surface area of a revolution, we take this formula and we calculate the centroid of the line L, which is just halfway along L, and we apply that to this. So here I've got to remember that I'm including the area of the end of the cone as well as the area generated when I rotate L around the x-axis, right? So that's one thing that can go wrong with this calculation, is that when you rotate L around the x-axis, obviously we're going to get a shape with a hole through the middle. So to find the total area of the cone, I need to include the base of the cone as well, which is what this piece is all about on the end here. And finally, the volume, I just do a direct application of this formula. The centroid of the area being rotated is the centroid of the triangle that's been rotated. I can look that up in the appendix and multiply that by the area of the triangle, which is just half base times height. So, moving on from the Papaskovna's theorems, we went on to look at centers of mass. So there's two ways that we looked at calculating centers of mass of an object. The first way is the integral way. This is if we're given a density rho, which is some function of x, so it tells us how the density of an object changes as the length changes or as we go along the object. So it might not have uniform density, and therefore we need to use the integral equation. We also need to know the cross-sectional area for this so that we can work out dv as the cross-sectional area multiplied by dx, and then hopefully get an equation in terms of dx, so then we can go ahead and integrate rho x, which depends on x, with respect to x. So we did an example of that in class. Dig that out and have a look if you've forgotten how to do that. The more typical question for this, however, is looking at compound shapes which are made up of objects that have different densities and sizes and therefore masses, right? So in this case, we work out the mass of each of the individual bits, we work out the x-coordinate of the centroid of the individual bits, and then we sum the products of those and divide through by the total mass. So for these results, we're often dealing with standard shapes again that we can look up in the appendix, and the only thing we need to remember here is how to calculate the total mass, which is just rho multiplied by the volume. So that's centers of mass. Again, there's an example of this which we did in class, where we looked at some different alloys of metal, I think, that were glued together. So again, dig that out if you've forgotten what to do. Moments of inertia. So what is a moment of inertia? First of all, well, it's the moment of a shape or an object about some given axis, and we can work out the moment of inertia about either the y or x axis, and we have some different formulae in order to work those out. And the answer should be given in the form of the radius of gyration multiplied by the area that's been rotated, right? And we can work out, as I said, the moment of inertia about either the y-axis or the x-axis, or we can work out the moment of inertia about a point, for example the origin here, and in that case we call that the polar moment of inertia, and it simply is just the moment of inertia about the y-axis plus the moment of inertia about the x-axis. So let's have a look at a quick example. If we're looking at finding the moment of inertia of this rectangle, so the rectangle has base A and height B, if you like, then what we do is we split up the rectangle into strips of width dx, and then we know some information. So each strip of width dx has area dA. The top of the rectangle is defined by y equals b, right, because the rectangle is of height b. So then we can just write dA as the width times the height. So the width of each strip is dx, the height is always b, so therefore dA is just b dx, and therefore we can plug this straight into the equation for moment of inertia about the y-axis. So we just integrate x squared with respect to dA. We've worked out what dA is, it's just b dx, so therefore we can work this out to get this solution here, ba cubed over 3. And if we do the same thing but finding the moment of inertia about the x-axis, we just flip the strip the other way, then we're integrating with respect to y, but we can work out what dA is in terms of dy, and therefore we can work out the moment of inertia about the x-axis. Now, I've chosen a shape like this, which is fairly standard shape, because I can go ahead and check these solutions in the textbook. And indeed, if you look there at the moments of inertia of a rectangle in Appendix B, you will find these two solutions. So that just validates that I've done this process correctly. And then finally, for shapes and volumes, we looked at what's known as the parallel axis theorems. And the parallel axis theorems allows us to use some standard results, which again are given in the appendices, to convert something that we already know into something that we want to find out, or that we don't know, right? So we can look up the moments of inertia of common shapes in the appendix about their center of mass. So let's just imagine that this blob is some common shape. In the appendix, we will be given the results for the moment of inertia about the center of mass. So it will be given the x dash moment of inertia about x dash, I x dash, so this one, and I y dash, this one. So these will be given in the appendices of the textbook. And what we want to do is use that to convert the moment of inertia about the axis, which is oriented about the center of mass, to some other axis that we want to calculate, right? So those shifts have got some distances associated with them, dx, so y dash has been shifted to y by distance dx, and x dash has been shifted to x by distance dy. So if we know that information and we can look this up, and the area of the common shape which is being rotated, we can work out the area, and therefore we can work out the moment of inertia about any axis system that we choose, right? So that's the whole point of the parallel axis theorems. It uses what we can look up in the textbook to convert it into something that we don't know. So please revise how to apply those theorems, and now we're going to move on to the final part of our review. So just before we move on, a good example of how to apply the parallel axis theorems. We did this example in one of the online videos. You can look this up, but we looked at the moments of inertia of this shape here, which is a compound shape made up of a rectangle with a semicircle on the end and then a circle cut out. Well, what we did to find the moment of inertia about the y-axis, in this case of this cutout shape with a cutout, was find the moment of inertia of the rectangle, the semicircle and the circle, and then put all of that information together. But basically we looked up the results for the moments of inertia about the center of mass of each of these shapes from the textbook, and then shifted it with these known distances by using the parallel axis theorem, right? So it's a good idea that you remind yourself how to do that. So finally for today then, we need to quickly recall some of the applications of all of this stuff. Sorry it's been a long video, and thank you for sticking with it, but I thought it was important to go through everything that we've covered just to refresh your memory. So the first application, I think we covered this quite early on in the course actually, was to do with springs. And we said if we stretch a spring out, then it exerts a pull force because the spring wants to contract back to its original length. So it exerts a pull force on whatever it's attached to. If you compress a spring, then the spring wants to spring back out to its original length, right? So it exerts a push force on whatever it's attached to. And we described this force, the magnitude of these forces, whether it's a pull or a push, based on the spring constant K, which is usually given in the question unless we're asked to find it, multiplied by the change in length. So you'll notice that this is in absolute value bars, so we're just interested in the positive value of the difference between the original length or the undeformed length and the deformed length, whether that's either a stretch or a compression. So what we do to solve a problem involving a spring is, if we're faced with a problem like this, where we have this mass suspended between two walls, this side has got a cable attached to it, and then this side is a spring. Well, we treat the spring as a cable initially, right, and find the tension in the cable. So we set up the problem like this. This is a very rough sketch of a free body diagram. But if we apply the equilibrium equations to this, we'll find the value or the magnitude of the tensions TAC and TAB. So we've just treated the spring as a cable for now. Then once we know what the tension is, we have the magnitude of the force, right, in the spring. So then we can treat it as a spring. So once we know TAB, we can plug in the spring constant to find the original length or the change in length, whichever we're asked to find, right? So that's how we deal with a spring. We treat it just as a cable at first, and then put the equation for the spring force in at the end. We looked at friction recently as well, and we said that there was two forms of friction. There's the static coefficient of friction and also the kinetic coefficient of friction. So the static one is the one that you use when the objects are at rest. The kinetic one is the one you use if the object is moving at a constant speed. And depending on what we're asked to find, depends on which one of these will be given in the question, unless we're asked to find it. N here is the normal force, which acts perpendicular to the surface that we're considering. So if it's on a slope, then it's acting perpendicular to the slope. It's important not to confuse this N with N for newtons, right? So in this example that I've quickly sketched down here, I've got a box being pushed up a slope of angle theta. Obviously the frictional force between the box and the slope is acting back down the slope, parallel to F, the force F, but in the opposite direction. So that's what I've sketched here. I've got F going up the slope. The normal force is perpendicular to the slope, right? So this is at 90 degrees. And the frictional force is acting back down the slope, and that will be the static coefficient of friction if the force F applied is not large enough to start shifting the box, right? And then finally, the weight vector always acts vertically downwards. So it's convenient in a situation like this to rotate the coordinate axes by angle theta, so that we don't have loads of cosines and sines floating around in our formulation. So that's friction. We also recently looked at axial force, shear force and bending moments, and the diagrams that correspond to those as well. And what we're doing here with these forces is looking at what's going on inside a member of a structure, the internal forces, right? And to work out what's going on, we cut the member between externally applied forces. So in the example that I've given here, I've got two ends of the member, A and B, and then I've got a force F applied halfway along it. Well, to work out what's going on with the internal forces in this member, I cut it once over here and once over here at these distances x. So I've cut it at some point x between 0 and L over 2, and then I've also cut it at some point between L over 2 and L. And then what I do to consider the internal forces is draw on the values, or these names for the various internal forces. So I've chosen to draw them all positive on the left hand side of the free body diagram. Remember, if I've cut it, then there's a corresponding right hand side of the free body diagram which I've chosen not to draw, but they will have the opposing directions, right, because they need to be equal and opposite. I've just chosen to draw the left hand side because I only have 3 unknowns on the left hand side in both cases, assuming that I know the reaction at A, given that I've applied the equilibrium equations and done all of this preamble first. So I cut the member twice, once here, once here. I apply the equilibrium equations to both of these left hand side of the sub free body diagrams, if you like, to find the unknown internal forces. And then if I've chopped the member at these values x, then I should get solutions for the axial force, shear force and bending moment in terms of x. And that then obviously describes how those internal forces change as I move along the beam. So then I can draw a graph or draw a schematic of how these 3 internal forces change as I move along the member. So I can just draw some graphs of those. And finally, the last class that we had before we started the review was on cables, when we revisited how to deal with cables when they have non-constant tension and they have this kind of sag associated with them, right? And we formulated how to find the shape of the cable. So it's a quadratic, obviously, because it's this curved shape, and this is the function of this line which defines the shape of the cable. The tension in the cable is given by this formula here, which we also derived, and that tells us that the tension in the cable is lowest at the is minimum at the lowest point, because x equals 0. Remember, what we do when we're formulating all of this is cut the cable at the lowest point and then set that as our origin of our coordinate system. So when x equals 0, this value t is minimum, so that tells us that the tension is minimum at the lowest point, and conversely the tension is maximum at the highest point, right? And then we also derived that really hideous equation for the length of the cable, S. So I've spared you all from writing that out again, but just be aware of where to find it and how to use it should you need to. So there we go. That's covered the whole course in, well, approximately an hour and a half, probably, something like that, an hour and 3/4. So if you're happy with all of that, you should be in very good shape for the final exam. Stay tuned for some more information regarding the final exam, and best of luck with your revision. If you have any questions, you know how to get in touch. Cheers.